The first question, let's discuss the assignment 2 solutions. The first question was, consider the system of figure. This is the figure, okay, with discrete time system as an ideal low pass filter with cutoff of pi by 16, okay, pi by 16 radians per second. So now if xc of t is band limited to 15 kilohertz, this guy here xc of t is band limited to 15 kilohertz, it has asked you like what is the maximum value of t that will avoid aliasing. Okay, second question is 1 by t is 10 kilohertz, what will be the cutoff frequency of this effective continuous time filter, this reconstruction filter which you have, what will be the effective cutoff frequency. We know in normal circumstances the effective cutoff is minus pi by t to pi by t, right? This is the cutoff of an ideal reconstruction filter. Now let's look at the solutions. So now first question was the xc of t is band limited to 15 kilohertz. That means your maximum frequency content in the input signal is 15 kilohertz. So if maximum frequency content is 15 kilohertz, you will have to sample it at a rate which is twice the maximum frequency content, right? So fs should be greater than equal to twice fm. Fs is 1 by t. So t 1 by t is greater than equal to 2 into 15 into 10 raised to 3. So this t will be less than equal to 33.3 microseconds. So this will be the answer of A. Second B question is, what it is saying is the x of n. See, when you have xc of t converted to gets converted to x of n is normalized to frequencies from minus pi to pi, right? Any when you transform any continuous time signal to discrete time, the discrete time signal frequencies get normalized from minus pi to pi, and they repeat every 2 pi. Now once you pass such a signal, discrete time signal, through a discrete time filter which has got a cutoff of pi by 16, your maximum frequency content, so y of n will have a frequency from minus pi by 16 to pi by 16 radians per second, right? This will be a normalized frequency again, pi by 16 to minus pi by 16 to pi by 16 radians per second. Since discrete time system is an ideal filter with cutoff, pi by 16, that's fine. So the cutoff, so the cutoff of so since your maximum frequency content here is pi by 16, the cutoff of this particular effective cutoff of this reconstruction filter is going to be pi by 16, from minus pi by 16 to pi by 16 t, right? So this is how it's going to look like, t, and from minus pi by 16 t to pi by 16 t. This is your reconstruction filter, or the effective continuous time filter filter cutoff is going to be. So if I plug it in, omega c, okay, omega c is pi by 16 t. Pi by 16 t is equal to pi by 16 into 1 by 10 raised to 10 into 10 raised to 3. So this comes to 6.25 pi into 10 raised to 2 radians per second, right? 100 divided by 16 will be 16.25, yeah, correct. So fc is going to be the omega c divided by 2 pi. Omega c divided by 2 pi will come to 312.5 hertz. Okay, now this one here, so then in the next question what they have done is they have only changed the value of t, the sampling rate. If the sampling rate is changed, only thing which changes is t value. So the same concepts apply, and you will have a pi by 16 into t. So this is the answer going to be 625 hertz, the cutoff frequency, or 12.5 into 10 raised to 2 pi radians per second. Clear? So now coming to the second question. Second question says that shows the overall system. This is the overall system which is shown, and where there is a system for filtering a continuous time signal using a discrete time filter. Okay, so this is the continuous time system using a discrete frequency response of the reconstruction filter. These are the frequency responses which are given, okay, and which is 2 pi into 10 raised to 4, which will pass everything from minus 2 pi into 10 raised to 4 to 2 pi into 10 raised to 4. Okay, Okay, now what it has asked you is nature of j omega is given 1 by t. Yeah, so the first part of the question is for xc of j omega, which is shown here. Find out, sketch excess of j omega and x of e raised to j omega. Okay, excess of j omega and x of e raised to j omega. That's what the question is. So let me just go to the question. So this is given, xc of j omega is given. Omega m is maximum frequency content is 2 pi into 10 raised to 4 radians per second, right? This is there. Now omega s is you have the what is given is t is 1 by 20 kilohertz. So naturally your omega s will be 2 pi into 20 kilohertz, which is 2 pi into 20 into 10 raised to 3, which is exactly twice omega m, right? If it's exactly twice omega m, the resulting excess of j omega will look something like this. It will repeat every 2 pi or every omega s. So your omega s is exactly equal to twice omega m. So this is your omega m, this is your omega s, this is your 2 omega m, and this is your minus omega m, and so on. This is minus omega s, and so on, right? So this is how your plot is going to look like, the spectrum is going to look like for excess of j omega. Now when you are converting this excess of j omega to x of e raised to j omega, right? Excess of j omega to x of e raised to j omega, you have to actually, this is x of e raised to j omega, this is x of e raised to j omega. What happens is omega s, the omega at omega s is mapped to 2 pi. Omega at omega m, since it's omega s by 2, this will get mapped to pi. So what will happen here is this will be 1 by t, the amplitude again will be same as 1 by t, okay, which is 20 into 10 raised to 3, and this will be repeating every 2 pi, and the spectrum will be from minus pi to pi. Okay, so this is your x of e raised to j omega going to be looking like. Okay, now coming back to the, this is your A question is answered. So now let's look at the B question. So this is A question. Okay, this is the spectrum at this point we have drawn, and we have drawn the spectrum at this point. Okay, now what it has asked you is for a certain range of values of t, the overall system with the input xc of t, and output yc of t, okay, in output yc of t, this system, or the overall system, looks like a continuous time low pass filter. This is how it looks like, it seems. This is H effective of j omega, and this is the overall system looking like. I mean, you convert it into discrete time, and then discrete time gets processed and converts it back, but overall it's basically a continuous time signal coming into a black box, and continuous time signal which is coming out of the black box, and the system response of this particular black box resembles a continuous time filter. This is the overall response of this continuous time filter looking like. Okay, overall continuous time, this resembles a continuous time filter which is low pass. Okay, and the frequency response of this H effective, if you see, is from minus omega c to omega c, minus omega c to omega c. Okay, now what we have to look at is what we see, this is what it should effectively look like. It should, like, when you give an input, the output should be yc of t, which is filtered version, right? Now what it is asking you is your xc of t is given to a black box, right? Is given to a black box, and this is the yc of t. Let's say this is your output. Now you supply some t. Okay, what is the range of these values of t, okay, for which this xc of t and yc of t, what are the values of t for which the impulse response or frequency response of this system looks like it's a filter, which is from minus omega c to omega c. That means it has to filter out the unrequired portion, and I mean whenever you give an input of a certain value, anything above a certain values should be cut off by that filter, right? And so what will be the range of values of t for which this will look like a filter? That is what the question is. Okay, now if you see, the whole second part of the question is, what it is asking you is to find out the range for which this guy, see, you have a system which is C to D, and then you have a filter which is h of e raised to j omega in the discrete time, and a d to c, right? So what exactly is happening is, there is a continuous time signal being inputted and continuous time signal which is outputted. Okay, now this acts like a black box. Although you are converting it into a discrete time, okay, the internals for the person who is looking it from the outside point of view, there is a continuous time signal going into the system, and there is a continuous time system signal going out of the system. So this acts like a continuous time system, right? Now what we want to find out is the values of t for which this continuous time system acts like a filter, such that it passes frequencies and blocks some frequencies above omega c. That is what we have to find out. We know that the h of e raised to j omega is a filter, is a low pass filter with a cutoff of pi by 4, right? We know that. So for what range of values of t does this act like this system acts like a filter, a continuous time filter? That is what we have to find out, right? Okay, so we know that the C to D here, the system here itself is like from minus pi by 4 to pi by 4 is what passes through. So y of e raised to j omega will always have a normalized frequency which is maximum of pi by 4, right? So we have this condition. So when do this guy map to pi by 4? Like when does the xc of j omega, which has got a maximum frequency of 2 pi into 10 raised to 4, right? 2 pi into 10 raised to 4, which is your omega m. When does this omega m map to pi by 4, right? So that is when omega s is 8 omega m. That is, omega s usually maps to 2 pi in the normalized frequency domain. So same way, what we want to find out is, when does omega m map to pi by 4? When you have omega s which is 8 times omega n, that time your omega m here will map to pi by 4. So this will be your x of e raised to j omega, which will map to pi by 4, okay, maximum frequency here. Now what we want is, if you want the system to act like a filter, what you want to see is those frequencies being cut off, right? Like some frequencies been rejected by this particular filter. That is what you want to see. So what you have is this omega m should be less than equal to, or sorry, omega m should be greater than equal to pi by 4. Only those, when you have this omega m, some frequencies coming out of this pi by 4 range, then they will be cut off, right? So that time you will understand that this acts like a filter. So that's why the first condition is the omega m should be greater than equal to pi by 4 t. So now you will get the lower bound on t. So there what omega m here is 2 pi by 4, 2 pi into 10 raised to 4. So this is how it is. Like you apply this system to this input to a continuous time h effective, and you get an output which is yc, right, j omega. Now when this guy, you know that internally there is a filter which is existing, which cuts off all the frequencies above pi by 4, right? So when your omega m is greater than pi by 4 t, those frequencies will be cut off. So then you will understand that this acts like a filter. That's why the first condition is omega m greater than equal to pi by 4 t. Okay, yeah. So then you get, when you plug in these values, you get t greater than equal to 8 into 10 raised to 8, which is 12.5 microseconds. That's the first condition. The second condition is, now you start decreasing your sampling rate such that these guys, this x for this excess of j omega, right? Excess of j omega is the replication, so they start moving this side and this guy goes this side. So omega s is decreased now. Omega s is coming closer to this omega m's, right? Now at a point at which forget about aliasing, there will be some unaliased frequencies, right? These unaliased frequencies, when you have omega s coming closer, these unaliased frequencies will be anything less than omega s minus omega m. Any omega less than omega s minus omega m, these particular frequencies will be unaliased. So any frequencies in this range will pass through, right? Will pass through properly. So when you have omega s minus omega m, which is omega s minus omega m, which is greater than equal to pi by 4t, right? Then some frequencies from pi by 4t to omega s minus omega m will be rejected, and this will act like a filter. So if you come closer, if you go below this, right, if your omega s minus omega m goes below pi by 4t, then what will happen is you will get some aliasing which will pass through the filter, which is pi by 4t, right? So that doesn't make sense. So that's why you should have a omega s minus omega m which is greater than equal to pi by 4. That's your second bound. So if you use that second bound, omega s is substituted with omega s minus omega m greater than equal to pi by 4t. So this omega s is substituted with 2 pi by t, omega m with omega m, and this you plug it in pi by 4t, and then you get a upper bound on t. So your t should be from 12.5 microseconds till 7 by 8 into 10 raised to minus 4 seconds. So that's your bound for which your system here will act like a low pass filter which is cutting off frequencies above omega c. Okay, here. So that answers your second question. Now coming to the third question. Now the third question is, this particular system is given. If you just go through this system, the third question, okay, so the range for which this is determined, omega c is a function of 1 by t. I think it will be a linear one. This one will I'll draw it separately. I missed that. Okay, so the third question is, in the system figure 4.241, xc of j omega is inputted, is given here. Okay, h of e raised to j omega is given here, and your T2 is the D2C, the continuous time filter, and then the yc of t is what is obtained, right? So now what you need to do is, these are given, and I want to sketch, you want to sketch xc of j omega and h of e raised to j omega are shown, and you want to sketch yc of j omega. So what we will do is, we'll start off with the first one, third A. Third A is here. So this is xc of j omega which is given, which has a length of maximum amplitude of 1. It's from minus 2 pi into 5 into 10 raised to 3 till 2 pi into 5 into 10 raised to 3. So first thing, let me draw x of e raised to j omega. X of e raised to j omega here will be a normalized frequency, right? So what we know here is 1 by t1 is given as 10 raised to 4. So your sampling rate fs is 10 into 10 raised to 3, which is 10 raised to 4 hertz. Okay. Now if you look at closely with this xc of j omega, this has got a fm which is 2 pi into 5 into 10 raised to 3. Now your fm here, this is your omega m, this is your omega m. Omega m is given as 2 pi into 5 into 10 raised to 3, where fm is 5 into 10 raised to 3. Now if you compare here, fs becomes twice fm, exactly equal to twice fm. So now when fs is twice fm, you know that in x of e raised to j omega, your fs 2 pi gets mapped to fs, okay, and the fm is fm gets mapped to pi. okay, because it's a fs by 2, right? Fm is fs by 2, so it's exactly half. So this is the plot you will obtain, and your amplitude will be 1 by t1. Okay, now you know that the filter, the discrete time filter which is present here, is discrete time system is a filter which passes only from frequencies from minus pi by t to pi by 2 to pi by 2. So this is what you will obtain at y of e raised to j omega with the amplitude of 1 by t1. Okay, and then since you have this guy has got d to c has got a t2, which is again 1 upon 10 raised to 4, right? So that is, you know that, so it's passing all the frequencies from minus pi by t2 to pi by t2. Yeah, so this passes all the frequencies from minus pi by t to pi by t2, right? And the amplitude is t2. If you see this, right, this gets converted. So this is your y of e raised to j omega gets converted to y of e raised to j omega t, okay, which is this guy here, okay. And then when it passes through this filter, only frequencies from minus pi by 2t to pi by t2 to 2t2 will pass through. And since t2 upon t1, which is this guy, t2 upon t1 is 1, so this will be, amplitude will be 1. So this frequency here will be pi by 2 t2, which is actually equal to 2 pi into 5 into 10 raised to 3, right? So pi, this is 2, this is pi by 2 into 10 raised to 4, which gives you 5 pi into 10 raised to 3. This will be the frequency here which will pass through. Okay, now the second question is, in the second part, t1 and t2 have been reduced, so the sampling rate is now 4 times fm, right? So what will happen in this case is they will be spaced out. So your h of e raised to j omega, sorry, x of e raised to j omega will look something like this, since the amplitude will be 1 by t1, and what will happen is your fs is spaced at 2 pi, and your fm, since it's fs by 4, you will get from minus pi by 2 to pi by 2. Okay, now this x of e raised to j omega is passed through a filter which is h of e raised to j omega having minus pi by 2 to pi by 2. This will pass through and you will get a y of e raised to j omega. It will pass all these things. If you see the previous case, there was aliasing happening, right? Here there were like some frequencies which were cut off. Okay, not aliasing, sorry, but some frequencies which are cut off. Here all the frequencies will pass through since you have increased your sampling rate. And then this will be this again will be passed through. This will be your hc of j omega, which is passing all the frequencies from minus pi by t2 to pi by t2, and your amplitude is t2. Here again, when you pass such a waveform y of e raised to j omega t through this, what you will get is from minus pi by 2 t2 to pi by 2 t2, and the amplitude will be t2 by t1, which is again t2 and t1 are same, so it's 1. And this frequency here will be pi by 2 into 10 raised to 4, which is 5 pi into 10 raised to 3. So if you see, this guy here gets compressed. Okay, so you had frequencies from minus 2 pi into 10 raised to 3 till 10 raised to 4 till 2 pi into 10 raised to 4, right? That was your original, but here it has, what has happened is this guy has changed it to 5 pi into 10 raised to 3, right? So it's basically 2 pi into 10 into 10 raised to 3 becomes let me just check it one more time. 2 into 10 raised to 4, yeah, so it's 2 into 10 raised to 4, right? This, so yeah, so t2 is 2 into 10 raised to 4, sorry. So this guy here will be pi by 2 into 1 into 2 into 10 raised to 4. So what you will have is pi into 10 raised to 4. Okay, So this is what you have from minus pi by 2, minus pi into 10 raised to 4 till pi into 10 raised to 4. This is what you will get, the spectrum of IC of j omega. In the third case, again you are increasing your sampling rate to 2 into 10 raised to 4 and the cutoff is reduced. Okay, so what happens here is 1 by t1 is from minus pi by 2 to pi by 2, since you have fs which is 4 times fm. So this is what you get as x of e raised to j omega, and then you pass it through a filter which is from minus pi by 2 to pi by 2. It passes through this from minus pi by 2 to pi by 2. Okay, and yeah, so yeah, so then this passes through pi by t2 to this guy here is your new y of e raised to j omega. Okay, and now if you look at it, this is your t2, this is pi by t2. hc of j omega has got a effective continuous time filter with frequency with cutoff from pi by t2 to pi by t2, and the amplitude is t2. So what you will get is t2 here is 10 raised to 4, so pi into 10 raised to 4 is what you have. Okay, so now once you pass through this, your y of e raised to ic of j omega will be t2 by t1, so pi by t2 t2, which is t2 is this, so 5 pi into 10 raised to 3 is from minus 5 pi 10 raised to 3 to 5 pi 10 raised to 3 is the frequency which were passed through, and t2 by t1 is half. Okay, so same thing here, you apply the same concept here, and this is what you get. You just go through this. So this, since here fs is twice fm, you will get a curve which is, will get a spectrum which is something like this with no guard band here, 1 by t1. Pass it through minus, this is your pi, this is your minus pi. Once you pass it through this, there will be cutoff, so you will get some part of the spectrum will be cut off. So you will get from minus pi by 2 to pi by 2, and then this will pass through here, and you will get a frequency from pi into 10 raised to 4 to minus pi into 10 raised to 4. Since t2 is what here, t2 is 2 into 10 raised to 4, right? So this is what you will get. Okay, so this is your third question. Now the fourth question, xc of j omega. Okay, so now coming to the fourth question. Okay, the fourth question is this is the spectrum of xc of j omega which is given. So if you see this, right, the maximum frequency content fm is basically not omega 0, it's the difference. Okay, so fm omega m is omega 0 by 2. Okay, so now what it is doing is, it is sampling at sketch the Fourier transform of x of e raised to j omega for omega less than pi. That is what is asked. So let's see this. So yeah, so the fourth question here is xc of j omega is given. So fs is omega 0 by 2 pi, t is 1 by fs. So now if you look at excess of j omega, what exactly happens is, for omega at this particular point, you will get the same curve back, right? You will get this curve and this curve back. Now at since it repeats every omega 0, for this particular point, what you are going to get is these curves here, this guy here and this guy here, right? And same way here. Now for omega equal to minus omega 0, at this point you will get this curve and this curve. So now finally what you have is complete triangle is what you get here. So if when you have x of e raised to j omega, since your fs is, if you look at fs, right, fs is omega 0, right, omega 0, which is exactly twice the omega m. So it repeats every omega 0. So this here gets converted into minus pi to pi. So minus pi to pi, this is the spectrum which you will get. Okay, this is the spectrum which you will get from minus pi to pi for x of e raised to j omega. Okay, so the second thing is, if I want to recover the original back, I'll have original is actually this guy right here. Original is this guy here, original. So I'll have to pass it through a band pass filter which looks something like this, from 2 pi by t to pi by t, from 2 pi by t minus 2 pi by t to minus pi by t, and from pi to 2 pi by t, pi by t to 2 pi by t. This is what you will need. There's a mistake here, so this is minus, okay. So you'll need to pass hc of j omega, will have to have a band pass filter something like this. When you pass this through the x of e raised to j omega is passed through such a filter, or such a d to c which is containing such a filter. So this is x of n, right? xc of t came in, gets converted to x of n. This is transmuted now. Now this guy is to be converted from using d to c converter. So the d to c converter, the reconstruction filter has to be a band pass filter which is from minus 2 pi by t to minus pi by t. So then you will obtain this back. Okay, so you will be able to successfully obtain this. And the range of t for which you can get the values is 2 pi by omega 0, t less than equal to 2 pi by omega 0. Okay, then the fifth one is very simple. I mean, you just have to go through that. I'll put up this assignment file there. You can just go through this. Okay, fifth one is sc of t is inputted to this multipath system, and it gets added up here. So you get xc of t, which is sc of t, which is coming from this point, and a delayed version of sc of t multiplied by alpha into sc of t minus td, right? So then you get, once you take a Fourier transform of this, you get sc of j omega, which is 1 plus alpha e raised to minus j omega td s of j omega. Since you know this, the Fourier transform of this is alpha into e raised to minus j omega td into sc of j omega. So this you multiply, and then this is xc of j omega. You know that the relationship between x of e raised to j omega, when you sample this guy, when you sample x of n, which is sampled version of xc of n t, you know the relationship is 1 by t xc of j omega by t minus 2 pi k by t. So just plug it in into this particular expression and you get this. Once you get this, this will be your x of e raised to j omega. Okay, that's what it was asked in the question, which says that, if you look at the question, it says that find the Fourier transform xc of t and Fourier transform of x of n in terms of sc of j omega. Okay, and then next it asks is find out h of e raised to j omega, right? H of e raised to j omega, assuming that this complete thing is one system. Okay, this complete thing is one system. Okay, I want to find out h effective of j omega, and then you find out, once you know that, convert it into h of e raised to j omega. That is what is asked. So for that, let me just go to the final page, which is this. So xc of j omega is known, which is from 0 to pi by t, right? Because this exists from 0 to pi by t. For everything else it is a 0. So now hc of j omega will be exactly your xc of j omega divided by sc of j omega will give you hc of j omega, which is this, from 0 to pi by t. When I convert this into j omega, e of j omega, I just have to replace omega with omega by t, and this is what you will get. Okay, so then this is from 0 to pi. Now once you take a inverse Fourier transform, this is your h of e raised to j omega, that answers your question, and then you take an inverse Fourier transform of that, and this is what you get. Okay, so okay, that's it then.